welcome to my lockdown heat transfer laboratory, my kitchen. Let's get started and have a quick look at some home experiments we can do to visualize heat transfer. Okay, I have here a cast iron pan and I'm applying steady heat at a relatively low flame. And so we'll assume that the flow rate of the gas is relatively constant and that the combustion rate is constant, and so that means our heat flow to the pan is also constant, but it's a low heat flow. All right, so what I'm going to do is I'm going to take this chopstick and use it to drip a little bit of water into the pan. All right, so we've got a couple droplets there. And we'll just zoom in, and you can sort of see, even though it's out of focus, that there's nucleation of gas at the very bottom of the droplet, and then it very quickly evaporates. And so, no surprise, you apply heat to liquid water, and it evaporates. So that's an example of mass transport, because water liquid is transporting into the air as water vapor. But it's also an example of heat transport because the heat from the pan is transferring heat to the liquid, which compensates for the latent heat required to vaporize it. And it's probably also adding a little bit of sensible heat to the steam that vaporizes. Okay, we're back with our pan, but this time we've got a much higher rate of heating as evidenced by a larger flame. And so this pan is a lot hotter in temperature. And when we add the water, we're going to see a slightly different phenomenon. If we add enough water, that is. All right, so we see those droplets forming. They're almost spherical, and they're actually sliding around on the bottom of the pan. There we go. So the water is moving here, and now what we have is a combination of heat transfer, mass transfer as the water is evaporating, but we've also obviously got some momentum transfer happening because there's movement. The gases that are vaporizing at the very bottom of the water droplet and forming a layer of vapor underneath the water are actually then heating and flowing around the sides of the semi-spherical droplet. And when it flows around the side, that's Einstein's Stokes flow. And what you see is the resulting movement of the water droplets. So that's a combination of all three transport mechanisms that we're going to study. What happens if we just dump a whole bunch of water in? Oh man. That looks to me like Voronoi patterns. Alright, I'm gonna go turn on my fan. Voronoi patterns result from nuclei impinging on one another, and given that this is the nucleation of a vapor phase, it's not really a surprise that we see this happening in my pan. Now that we've seen heat, mass, and momentum transport in action, let's put it on a grid and think about it with an analytical lens. We lump heat, mass, and momentum transport together into this general category of transport properties because they have a lot in common. To begin with, they all start with a molecular level flux quantity. And so for heat transfer, that quantity is conduction. If it's momentum, you've got the transfer of momentum through Newton's law of viscosity, which is again a molecular flux. And if it's mass transport, you have Fick's law of diffusion. So the molecular flux is literally that quantity, whether it's heat, mass, or momentum, transferring between individual atoms or molecules in a system. And that's why we call it a molecular flux. All of these transport phenomena also have an associated diffusion coefficient, which has the same units in all instances, meters squared per second. They also exhibit bulk transport, and this is kind of intuitive to us For momentum, this is water flowing. For mass, you don't really see mass convection independent of momentum convection, actually you don't see heat convection independent of momentum convection. So the bulk transport properties are all associated with momentum transport. Finally, we see transport between phases, like heat going from a solid cast iron skillet into liquid water. And in that instance, there's always a resistance to transport. And so understanding what the boundary condition is at that interface enables us to make accurate calculations. Let's review what you already know about steady state and transient problems. At steady state, the temperature distribution, or the temperature profile, is constant. And for a transient problem, it varies. In a steady state problem, there are variations in the temperature profile, but they're always going to be spatial variations. A transient problem may have spatial variations, but it doesn't necessarily have to. A steady state problem is not going to have variations in the temporal domain, which is the time domain, because it's at steady state. But a transient problem certainly will have temporal variations. Steady state is most commonly associated with a continuous chemical process. You can think of other processes as well. Transient problem is most commonly associated with a batch reaction, or it can be with startup or shutdown of a process. And finally, the mathematical complexity of a steady state problem, you only have spatial derivatives. If you're working in one dimension, you only have one spatial derivative. It can be second order though, do note that. For a transient problem, you have at least one temporal derivative and spatial derivatives. And so it means that it can be more complex, but it doesn't necessarily need to be. Finally, let's discuss steady state and transient processes to prepare you for your design project. On the left-hand side, we have a reactor, and you see two reactants are flowing in, gases are venting out, and a product is coming from the bottom. You also see that it has a cooling jacket. So you might be tempted to assume that this is a CSTR, and this would be the same schematic you would use for a CSTR, but it could also just be a batch reactor, and the reactor is charged, the reaction completes, and then the reaction discharges. So be very careful if you are the person designing a reactor in the design project. It is quite common for people to accidentally design their batch reactors as a continuous stirred tank reactor, because that's kind of what you're used to doing. The difference is not really going to be so much in the hardware setup, it's going to be in the calculation. So for a batch reaction, you've got the enthalpy of reaction is going to be changing the temperature of the reaction, and so that's why you would put a cooling jacket on it to try and maintain an isothermal temperature. Whereas a continuous process, you might actually be able to design it so that it doesn't need a cooling jacket, so that it's exchanging heat with another part of the process. On the right-hand side, we have a notorious distillation column, which is obviously a steady state process. I should write that here. And I don't think if you have to design a distillation column, you'll have any problem recognizing that it's a steady state system, because you've done this already in CPE 270. So this is just my word of warning. Be careful to note, first and foremost, is your process steady state or transient? Thank you for watching Chapter 1, and I'll see you for Chapter 2.